All right, what's going on? It's your boy Hank Hackerson at Hank Hacks Hackers, and we are continuing down our security engineer pathway today. This is going to be episode 9, which goes inside of the network and system security module of the security engineer pathway of TryHackMe. And today's room is called the secure network architecture. And this is what our outline for today looks like. So we have the intro, network segmentation, common secure network architecture, network security policies and controls, zone pair policies and filtering, validating network traffic, addressing common attacks, and the conclusion of the room. All of these things are going to be timestamped in the description below, so you can bounce around and check out individual portions if you want to. But apart from that, this is literally what we're going to be talking about today. The first specific room of network and system security on episode 9 of the security engineer pathway. If you are studying for your security engineer or security analyst, Pentest Plus, ethical hacker, any of those things, then I do encourage and invite you to like and subscribe and turn on the notification bell so that you get notified the next time that a video comes out from this channel. There's also the SOC Level 1 playlist that already is completed, and that's for the junior security analyst, and just a lot of really, really good stuff for security analysis that you can find that on our channel. And then there's the Pentest Plus. It's not complete, but there's a good number of videos. I think there's maybe like 30 something videos in the Pentest Plus playlist. And yeah, so that's kind of where we're at right now. So all of these things will actually be directly applicable to your certification exams, because I did take my CYSA and it was directly applicable to everything that was covered in that examination. So I know it'll be useful to you in there, but it'll also be useful to you in your day-to-day job as an analyst or an engineer or anything of the sort. So I think you will definitely get a lot of value from this channel. And then just for me, it would be really awesome to have you as a part of the community so that I can see, just help grow the community. And if you have any questions, you can drop them in the comments. I'll answer to them. I love our community. It's been a very, very fun process to do all these things. And it's nice to see that people are finding value from it. And, if I can help you, I'll definitely answer all your questions and try to even make videos for you. So that is it. And without further ado, let's jump into the introduction of the secure network architecture room. So, I mean, there's not really much going on in the intro here. So, networking is obviously one of the more critical components of the corporate government enterprise type of environment. And from a security standpoint, it can be overlooked typically because we're so focused on softwares and maybe even users or systems or something like that. Nobody really, or few people, look at the network itself as a whole. So if you have a really well designed network, then not only do you actually get internet service, but you also get redundancy, optimization, and security. A lot of network appliances like Cisco routers and Cisco switches and stuff like that, they come, especially if you get like the really fancy ones, the expensive ones, they come with a lot of good security embedded in them that kind of prevents a lot of hacks to take place if those things didn't exist. So if a switch goes down in a good network, if a switch goes down, packets can be redistributed through another route with no loss in uptime. If a web server is compromised, it cannot traverse the network and access important information. So a system administrator should be confident that their servers are secure. If a random device joins the network, so you got to keep track of all of your devices, right? So if something gets plugged in or if somebody shows up in your list of devices, you should know what's going on and then immediately go and find that. And this is something that's like a big deal, obviously, in the military environment and the government environment. If you plug in a wireless access point that is not supposed to be a part of that network, within minutes, they'll come and find it and destroy it or arrest you or whatever. So these types of things are really important, right? So everything is what we're going to be talking about in this particular room has to do with these objectives specifically. But it's a big one. This is one of those big conversations that we're not going to cover everything inside of this room, and we're going to probably look at some surface level stuff inside of this room. So we're going to be going through principles of secure network architecture, implement common security, network security concepts and protocols, and understand the environment and potential threats to a network. You do need to know a basic understanding of networking terminology, so I do recommend you go into that. I don't have any videos on that, but there's a lot of good stuff out there. And so if certain things don't make sense to you in this video, feel free to just pause the video, do some Googling, and read up on it so that everything else can connect for you and make sense. So there's our intro, and let's jump into the network segmentation. All right, so the need for secure segmentation. There's a few different things that you need to be aware of when it comes down to network segmentation, segments of a network. So let's consider a particular scenario that would help us kind of understand what a subnet seems to be and why we need to segment our network and so on and so forth. So let's say that you have a client that brings their own device. It's called BYOD, bring your own device. The client's device was infected with a remote access Trojan that will attempt to traverse the network when the device is connected to and exfiltrate any sensitive information. So with subnetting in place, there's no restriction in place that the infected device there's no restriction to prevent the infected device to connecting to other things and routing or finding your different portions of your network and stuff like that. So it leaves sensitive information and computers and servers and everything open to whoever this unknown device is that this person just brought them in. So how do you fix that? There's something called a virtual LAN, a VLAN, and it's used to segment portions of the network to at the layer 2 level, which is the IP address level. Or no, I'm sorry, layer 2 is actually the MAC address level at the layer 2 and differentiate devices, right? So VLANs are configured on a switch by adding a tag to a frame. 802.1q, a .1q tag will designate the VLAN and that the traffic is originating from. So this is the Ethernet data frame that you'll see right here. And then the VLAN data frame that has the VLAN tags that will get associated with it. So the 802.1 tag provides a standard between vendors that will always define the VLAN of a frame. For example, if our switches are Cisco and the routers are Juniper, then they can send tagged frames and digest them equally because it's standardized, meaning it's uniform across, doesn't matter what brand equipment you're using. So we're going to go and configure these things. As an example, we're going to go and configure these things. So we're going to use the open source switch, which is Open vSwitch. And from Open vSwitch, I'm just going to open it up inside a thing right here. I wonder if I have to download this. Let's see if we can just kind of see what the whole thing is, and maybe they'll have it available to us later on in this room. So first we're going to look at the default configuration of the switch. So you do, once you're inside of your command line, you do OVS vsctl show, and then to add one, you can just go and do set port, the interface, and then any kind of a port number. The tag should now be listed under the sub interface in the configuration. So if you go to the port ETH1, and you'll see a tag 10 attached to interface ETH1. So now we have the first interface configured, and we can do it so to tag their frames. So if we don't know where the VLAN traffic originates from, for example, traffic from the virtualized device or the network, what do we do in that situation? So tagging unknown traffic. So the native VLAN is used for any traffic that is not tagged and passes through a switch. To configure it, we have to determine what interface and tag to assign to it, and then set that interface as the default native VLAN. So this is what that would look like in the command line. So you set a port for this interface, tag is going to be 10, VLAN mode is native, and it's untagged. So now all the traffic that goes through that should be tagged, even if it doesn't have even if it doesn't have known origins, even if it's unknown. So routing between VLANs. So what's the capacity, or how does a VLAN connect to the internet or other resources in other VLANs? So since they're segmented, they can't communicate outside of their tagged devices. So since routers are used to communicate between traditional networks, you can use routers to route between the different VLANs. So it's not that complicated, right? Before all the fancy stuff that exists nowadays, network engineers would physically connect a switch and a router separately for each VLAN. Nowadays, we can do it through ROAs, so a router on a stick design. And so VLANs are configured to communicate with a router through a designated interface, and then that specifically is called a switch port. So a designated interface of a switch is called a switch port, basically a little hole in the back that you plug your Ethernet cable into. The connection between the switch and the router is known as a trunk. So a trunking protocol is what you hear very frequently. So the connection between the switch and the router is a trunk, and then that trunk goes out of the switch port and it goes to the router. And if this is done physically through the wire, right? VLANs are routed through the switch port, requiring only one trunk or connection between the switch and the router. Hence it's called on a stick. So before configuring the router, we have to configure a trunk on a pre-existing connection. And in our demonstration environment, trunks are configured by the default as bridges. So a trunk can also be referred to as a bridge. So this might get a little bit complicated, but just kind of try to keep track of these terms, right? So each vendor configures their trunks and switch ports differently, and some even with proprietary protocols. So you would have to go look at their individual documentation to try to figure out what their protocols are and how they configure their trunks and their switches. This is what we would do on the OVS. So you would do add BR and then BR0, add port for BR0 on this interface, and then tag 10. And now we can configure our router to route tagged traffic between VLANs. And as mentioned, we can introduce tags because 8021Q tag is standardized, and we only need to tell our router how to configure its switch port that belongs to just that router, and then what tags to accept for that interface. Because all the tag traffic comes from a single connection, the router has to be able to keep each tagged frame separate because it's all coming from one connection, and it should, otherwise it would get they would clash each other. I forget, I think it's called broadcast clashing or something like that. I forget the specific terminology, but so this specific action right here, so since it needs to be able to keep everything separate, that's accomplished using virtual sub interfaces. And this is going to act very similar to a physical interface, but it's just virtual. And so that is called its ID. So the VLAN's ID is its sub interface. And the syntax for that is the name of the VLAN, and then, or excuse me, the name of that specific sub ID, the sub interface. And then you have the VLAN sub interface ID. So you have its name and then its actual ID that's attached to it. In this example, we're going to be adding a new virtual sub interface and configuring the addressing for it. We're going to be using Vios, and let's go and check that out. And this is Vios. It's open source. There's a buy now, but it should be open source based on what they just declared over here. So maybe ever since they made that, it became a paid resource. So you have, Vios set interface Ethernet on this interface. VIF 10 description, yada yada. Interface Ethernet, same thing. The address is that. And then notice that they did 1/24 to say that we're going on this particular subnet. And then there's 24 bits, I want to say, because 24 bits, because each byte is 8 bits. Yeah, I think it's bits. If all went well and was well configured, we should be able to route traffic between VLANs while keeping traffic tagged and isolated. So are they really isolated though? They are physically, but because routes exist between them, there's no security boundary. So that's where all of this is how it all connects to security engineering, right? So they're physically isolated, but because there's routes between them, meaning they can communicate with each other, there's no security boundary and they're not necessarily isolated. So as long as a route exists between those two VLANs, they can all communicate between each other. And then we can now talk about what we need to actually talk about for this particular room and this task. So securing VLANs and introducing the concept of zoning. So creating zones for VLANs and what to do if something actually happens inside that VLAN that you don't want it to go into the rest of your network. So analyzing the configuration, this is what it's going to look like. This is apply what you learned to analyze the configuration given in this output below. So we have this whole thing right here, and you have the ports on the different interfaces with their tags. And then at the bottom, we have the bridge BR3. Okay, so how many trunks are present in this configuration? So let's see that. So being that a trunk can also be referred to as a bridge, we have one bridge, two bridge, two bridges, three bridges, and then we have four bridges. So that would be four trunks. And then what is the VLAN tag ID for Ether12, ETH12? So ETH12 right here, port ETH12, the tag ID is 30. And there is that. So fairly straightforward. I mean, we don't need to know all of the in-depth stuff behind all of this, but you do need to understand that a bridge is technically a trunk. In this particular case, we have four bridges or four trunks, meaning that there's four VLANs, and inside each one, there's a particular interface. Inside the BR0 right here, there's way more than the rest of them, so this is probably the busiest part of their network, so on and so forth, right? So not overly complicated to understand. There's a lot of jargon and there's a lot of technical data that they shared with us because it's important for us to know these things, because even if you are in security, you still need to understand networking. So that part's very, very important. But that's neither here nor there. So next piece is going to be the common secure network architecture. With the introduction of VLANs, there's a shift in network architecture design to include security as a key consideration. So this is where we come in, right? So security optimization and redundancy should all be considered when designing a network, ideally without compromising one for the other. This brings us to a very important question. How do we properly implement VLANs as a security boundary, which is now going to bring in security zones and zoning? Security zones define what or who is in a VLAN and how traffic can travel in and out of that VLAN. Depending on who you speak to, every architect in a network may have a different approach to the language or requirements surrounding security zones. We're going to talk about the most commonly accepted security zone standards, and then thankfully we're going to be looking at it in a minimalist approach. And this is, by the way, consider the fact that they think that this is minimalist, right? So this is the table of commonly standardized zones, and the zone, and then the explanation of the zone and an example of the zone. So you have external, which is everything outside of the network or asset control, devices connecting to a web server. Demilitarized zone, you'll hear this a lot, DMZ, a demilitarized zone. It separates the untrusted network from the internal network. So our demilitarized zone can be accessed by the public without any kind of login or any kind of special credentials or anything like that. And that would be a remote user or a guest, a public server, right? It's available to the public, BYOD, bring your own device. You have the trusted zone. So internal networks or devices, they've been placed in the trusted zone if there's no confidential or sensitive information. So that could be a workstation or a B2B, business to business communication. You have restricted, which is a high risk server or database, which is your domain controller, right? Or information, or a database that has client information on it. So nobody should be able to access that except key people inside of the organization. Then you have management, that belong to, these are basically any device or service that belongs to the management department. It's less commonly seen, and can be grouped within the audit zone, which is the very next one right here. And so virtualization management, backup servers, all that stuff. And then you have the audit zone, any device or service dedicated to security or monitoring, and it's less commonly seen and can be grouped with management. And that could be a security information and event manager, telemetry. Ooh, I've never even heard of that. I mean, I have heard of it, but I have no idea what it is. So maybe we'll talk about that in a little bit. While security zones mostly factor in what will happen internally, it's equally important to consider how new traffic or devices will enter the network, be assigned to the network, and of course interact with internal systems. Most external traffic, so HTTP, which is internet traffic, mail, right, email, they stay in the DMZ, the demilitarized zone. But what if a remote user needs access to an internal resource, and we need to easily create rules for resources that a user or a device can access based on their MAC address, their IP address, or something like that. And we can then enforce those rules from the security controls inside of the network, and we're going to be talking about that in the next task right here. So you have external and wireless is everything like a regular person, or this icon right here represents a hacker or an attacker. And then you have, from the external wireless network, there's a firewall right here. And then you have the demilitarized zone that has the stuff that you can use, that can be publicly viewed. But again, there's a firewall between this and the trusted zones, which is could be your Linux server, it could be any kind of web server, it could be your workstations, anything like that. And then you have a final firewall, which is going to the restricted zone, meaning these are the people this is the zone that only domain controllers or domain administrators or executives, all those people can access. So with each level, there is another firewall and another firewall and another level of security that this particular person, this hacker right here, they would have to go through to be able to get access to what's going on. So security zones and access controls will physically direct how and where traffic goes. But how is it decided what resources users or devices have access to? Traffic rules are often governed by company security policy or compliances, equally as security controls that determine their permissions. So we've established a system to approaching the design of a VLAN, but how can we practically implement this? So that's what we're going to talk about in the next task. So from the above table, what zone would be a user connecting to for a public server to be in? And so this is probably going to be either the external zone or the wireless zone. So let's try external. And that's not it. So let's try wireless. That's not it either. So what zone would a user connecting to a public web server be in? Didn't I type in external? Maybe I misspelled external or something? But yeah, it is external. I mean, what the hell? Anyways, from the table above, what zone would a public web server be in? So a web server would be the public server right here. So it's a DMZ, a demilitarized zone. There you go. And from the above table, what zone would a core domain control? That would be restricted. I already know that. Restricted. So there we go. We have our zones, and we can kind of understand some secure network architecture. So let us now go into the security policies and controls for these things. So how do you enforce secure architecture design, right? If there are routes between VLANs and they're supposed to be separated, how is it possible and appropriate to access restricted stuff? Or how do you restrict access? Or how do you grant access, right? policies, basically. They aid in defining how network traffic is controlled. A network traffic policy can determine how and if a router will route traffic before actually routing it. IEEE, Institute of Electronics Engineers, has standardized a handful of access control and traffic policies, such as quality of service, and there are many other routing traffic policies, obviously, that aren't standardized by IE, but they're commonly used by a lot of vendors, right? So we're going to be focusing on traffic filtering and introduce network policy concepts. So traffic filtering. Before defining what a traffic filter is, let's discuss what one of the more common standards is, which is access control lists. So an ACL is used as a loose standard to create a rule set for different implementations and access control protocols. We're going to use ACLs within a router to decide whether to route or drop a packet based on the defined list. And ACL contains ACEs, the access control entry, or rules that define a list's profile based on predefined criteria, source address, destination address, MAC address, probably, a bunch of stuff like that. Once defined, we can use the access control list for several vendor-specific implementations. For example, Cisco uses ACLs for traffic filtering, priority or custom queuing, and dynamic access control. Traffic filtering provides network security, validation, segmentation by filtering network traffic based on predefined criteria. And so now we've defined what traffic filtering is. So let's look at ACLs, how to implement an ACL and traffic filtering. To do this hands-on, we're going to look at BIOS again. And the access list policy is the platform's most basic implementation. So it's going to be broken down into a few things. First, we're going to create the new access list, define the ACL number. So you set the policy access list, and then you give it a number between 1 and 2699. Then you set the description of it. So set policy access list, the number that you've assigned to it, and then give it the description. And then you use the description option or parameter, I guess, and then you give whatever the description is supposed to be. Then you create a rule for it. So now you have the same thing, access list, the number. Now you have a rule for it and the rule number. And then here's the action that the rule allows you to do. You either are permitted to do something or you're denied from doing something. Then you set a criteria for parameters for the rule to actually enforce or match. And this is where it comes into, so, this is the rule, it permits, and then this is the list of destinations that are permitted, or the list of sources that are permitted. And would it be anybody? Is it a specific host? Is it an inverse thing? Is it a network that gets access or, is permitted, right? So now we have an ACL, access control list, and an ACE that is actively being enforced by the router, right? So you have the access control entry that is assigned to an access control list, right? So the ACL is defined as the ACL number, and it's made of separate rules for the entry that describes the behavior of that. And each entry can determine the action, the destination or the source address, and the specific address range to trigger that entry. And this is what it would look like. This is a valid SSH request being permitted by the list. So the IPv4 source address is this, destination address is this. So literally same freaking thing. TCP is the protocol that's going to be used. Checksum is this, validation disabled. Header checksum is unverified. The source is 12.209, 12.209, or 212.209. Transmission control, source port 35560, destination port 22, sequence 1578, acknowledge 1670, length is 148 bits, source port 35560, destination port 22, right? And then so these are the actual commands that go into. So set the policy for access list 1, rule 1, action permit. and then set the policy for access list 1, rule 1, that the source IP is going to be 10.10.212.209, okay? Now this is what a denied list would look like. Basically, everything that you saw previously, the destination port in this case is going to be 2 instead of 22, but pretty much everything else is exactly the same that you just see right here. And then what we see as a command is that now it's going to be a deny action instead of a permit action, and exactly the rest of it is exactly the same. So if implemented correctly, the router should now drop or accept packets based on the source to destination address. Is it the best solution? If we want a public server in DMZ and be able to ensure that only HTTP traffic originates from it, what do you do? So what is the specific host that needs specific protocols to be open on a server? And the router can only provide a limited number of extensibility for security. So now we need to address that specific scenario, right? So first we got to answer some questions down here. So it says below is each packet. So we see that we have a structure of an access control list and what it would be like for in a packet. And we're going to analyze a few packets to determine if they will be accepted or dropped. So each packet, we have it right here, required. There's a ACL that's attached to it. And then we're going to answer these questions. So according to the corresponding ACA policy, will the first packet result in a drop or an accept? So this is our packet. Okay, so 22, all this stuff is very simple. So this is the access control policy. It says, is it going to be dropped or accepted? And so it's permitted, so it's going to be accepted, right? So accept is permit. Based on the second one, is it going to be dropped or accepted? So this is the packet. And then so let's look at, and then you see deny. It's it's pretty straightforward, right? So it's going to be dropped. That's it. Very, very simple. So now we got our understanding of security policies and controls for the network. So let's go look at zone pairs. So a zone pair policy and the filtering of the zone pair. And we actually have a website attached to this. So let's see what that's going to be like. All right, so we looked at security policies and controls. Now we need to look at zone pair policies and how those things get filtered. So a traffic correlation is standardized as the state of a packet. So what is the protocol, the process, the direction that it's going from where to where. We must employ a firewall to parse the state of a packet and enforce the policies based on that state. So a firewall, basic network firewalls, they do two things. They're stateless or stateful. The category is determined based on the ability to consider the state of a packet. For example, an access control list used in that previous task would be regarded as a stateless protocol. A stateful firewall can better correlate information in a connection. So it allows the firewall to filter based on ports, protocols, processes, other information from a device. And for this, we can go into the extending your network room, which I don't know if I've done. Have I done this? I think I have. Oh yeah, firewalls, practical firewall, VPN basics, networking devices. So I think this was one of the pre-security or like one of the beginner stuff. So extending the network, introduction to port forwarding, and we have firewalls 101. What is an actual firewall? And then you have the practical that we had to do to capture a flag. And we have the VPN basics and what it actually does using encryption and how it secures a connection between certain things. And you have the, what do we have here? This is the LAN networking devices. So the stuff that goes inside of a local area network. So you have your router, you have the layer 2 switch, you have all the computers that are attached to it. Then you have a router, and then you have another switch, and it has two different VLANs now that are coming out of that switch. So it shows us a couple of examples of a networking device, and then you have the network simulator that we had to go through to try to pass data packets or frames from these devices so we can get some access. So I am not going to go into the details of that. You're more than welcome to go through. Actually, I think this was probably one of the free rooms too. Let's see. It usually tells us at the bottom if this was a free room or not. No, this was a subscriber only room. But you can, just based on what I covered right here, you can probably get some nice information from Google or from Gemini, the Google AI, or some YouTube videos or something like that. So Before configuring the firewall, we need to consider how we can apply the requirements of zones to the actual firewall rules. So how can we define different actions based on the protocol and source destination zone pair? So or the zone. So you get a zone pair out of that. So the zone pair is a direction-based and stateful policy that will enforce the traffic in a single direction per each VLAN, hence a zone pair. So for example, a demilitarized zone to the local area network, and then vice versa, the local area network to the demilitarized zone. It's going in just in one direction, right? Each zone is given a topology. Each zone in a topology must have a different zone pair for each other in the topology in every possible direction. This approach provides the most visibility from a firewall and drastically improves the filtering capabilities. So we're going to use VIOS again of configuring a firewall for zone pairing. And before defining the pairs zoning policy, we have to add a common name and default action for each one of them. And we're going to go look at the last two that we were routed through the trunk and divided through the sub interfaces. So the interface.VLAN number is the naming for it. So for example, ETH0.30 is going to be one specific VLAN, right? VLAN ID. So below is an example of setting up a default action for the DMZ and assigning it to the VLAN for the common zone name that we have over here. So set zone policy zone DMZ, and then default action is drop. Then it's going to say the DMZ interface is ETH0. So the zone policy for the zone DMZ is the default action is drop everything, right? And then the DMZ interface attachment to that is going to be ETH0.30. So we're going to repeat this for each VLAN or zone that's been defined in that network. And then before we can begin addressing each one of this, you need to be understanding this particular topology. So you have the demilitarized zone, you have VIOS, which is going to be doing the job that you want it to do. You have the wide area network, and then you have your local area network. And your wide area network is the internet, basically. And then you have your local area network, and then you have your demilitarized zone. And all of this is going to be going through VIOS. So each zone is going to have a corresponding pair to every other one. To define it, we need to write down each possible pair and protocol that we're going to apply. So this is an example for each zone pair in this particular topology and what possible protocols could be looking like. So you have the LAN, the local area network, that has the zone B attachment. So it's the zone B could be the wide area network, the internet, the local network, which is itself, and then the demilitarized zone. And so the protocol to the wide area network is going to be ICMP, and then it's going to be dropped. So the action is to drop that. In its own network, nothing is going to happen. And connecting to the demilitarized zone, nothing is going to happen. The wide area network to the local area network, ICMP protocol, is going to be accepted, meaning that the local area network should be able to access the internet, but the internet should, in this case, it's saying the internet shouldn't be able to access the local area network, but the local area network, in this case, should be able to access the internet. And you have the WAN to local, nothing, WAN to DMZ, nothing, right? And then you have local to the LAN, nothing, local to WAN, nothing, and local to the DMZ, nothing. And then finally you have the DMZ to the LAN, and that should be through the HTTP protocol, and that would be accepted. Then you have DMZ to the WAN and to the local area network that have no rules attached to them, right? This is it for this particular topology. So it gives us an understanding of the expected behavior and a good plan to begin configuring the firewall. So not all traffic is IPv4. Depending on the network configuration, you may also need to consider IPv6 rules, which have very different looking IP addresses. So because of the default action that we set, any protocol that originate on the network and are not defined are going to be dropped by default. So we're not going to go over each rule set. Instead, we're going to cover one zone pair in each direction and then test that behavior working as, hopefully that it works as expected. So we're going to configure the LAN and the WAN zone pairs. And after the example, hopefully you'll be confident about configuring something, a small, small topology, a small zone for yourself. So for all BIOS firewall rules, we have to begin by defining the default action and the state rules. And then we're not going to cover the intricacies because that's probably an entire module or pathway just by itself. So instead of repeating 7 commands, we just rely on the BIOS configuration to define the rule. So this is the example. The top of it is going to be the LAN WAN. This is the rule set specifically. So what are they calling it? The configuration. So we have to begin the default action. There you go. The default action and the state rules is what we're doing. This is what it is. So the name of it is the LAN WAN. The default action is to drop, and then enable the default log. And then the rule 1 is accept, state, established, enable, related, enable. Okay. Rule 2 inside of this is drop, enable the log, and invalid enable for this particular state. So anything that's invalid, enable that. Established connections, enable that. Related, enable that. Meaning that all of these things should go under this particular rule. In this particular action, you have these two, the established and related connections should get accepted. And then if it's invalid, then it should be dropped. So enable over here means that enable this rule for this state. Enable this rule for this state, right? And then you add the rule for ICMP. So rule 100, the action is to drop, and then this is the comment. So define the action for the rule. The log is enable, so enable logging to track connection attempts in BIOS. And then the protocol is IPv4 ICMP, so the protocol to monitor and enforce the action on. And then now we have the first zone pair rule set. Now we can create the rules for the zones from the WAN to the LAN and the LAN to the WAN. So this is the rule set that we had previously. Rule 2, rule 100, this whole thing is our rule set right here. So now we can move into the zone pair. So the zone pair is now, do we have it? Oh no, you know what? It's it's actually, it was added to the piece right there. So it's under rule 100, which is the action IPv4 yada yada yada. This was the actual zone pair rule set. So this is the zone pair rule set. This is what the completed version looks like. That's what we're looking at over here. So there you go. Zone pair is now defined with appropriate actions and steps, and we can combine the rule set with previously configured zones. So at the beginning of this, we configured zone policies with the corresponding interface and zone name. So we have the zone policy for the zone, which was the zone A, from zone B, and then firewall, the name of the firewall, and then the rule set name. So we're going to set the pair for the LAN WAN and WAN LAN pairs. So set zone policy zone LAN from WAN, firewall name LAN WAN. And then set zone policy zone WAN from LAN, firewall name WAN LAN. And we have the official first pair of this, right? So to test the configuration, we can just send a ping in both directions to ensure that the firewall is dropping or accepting the packets that you need. And creating something from scratch, it just requires that you pre-plan everything before you start putting the commands into the interface, the command line interface. So we're going to do this live in this particular situation through the view site exercise at the very top. We have our source, the DMZ, the LAN and the WAN, destination, and then the protocol, so on and so forth. So we need to configure our whole thing and then capture a flag at the end of this. So I am now going to click the view site button, and it's going to open this up for us. Reduce the configuration as the visualize packet flow. It will help you set up the correct configuration to get the flag. So what's our tutorial? Please select a blank to view its corresponding options. Okay, next. Please select the blank to view the corresponding options. As soon as a blank is selected, you can choose an option here. Okay, next. And then once the blanks are filled, you should run the workflow to see whether or not it works. Next. And then what is this? We have the visualization of the packet flowing in the diagram. Okay, so DMZ to WAN. This is kind of what it looks like, I guess, at this point without anything happening. So zone policy, zone, where are we at? We're at the bottom right here. And set zone policy zone, and then the action that you want, and then the zone policy zone, so on and so forth. So in this particular case, we have the DMZ, which is going to be the source, destination is LAN, HTTP protocol, accept is the action, the default action is dropped. So set zone policy here, it's going to be DMZ, and the default action should be drop. So the zone is going to be DMZ here, the default action is going to be drop, and then go back here, and so DMZ connecting to the inner interface is ETH010 right here. So ETH010. And the next one again is going to be, now we're going to look at the LAN in this particular case, and the default action for that is going to be drop, and the interface for the LAN that needs to connect that to is going to be the ETH020. So we're going to go here and click that. So that's our first set of rules right there. And then so the set firewall name in this case, DMZ LAN. So DMZ LAN, there we go. And the description in this particular case is going to be, I guess, DMZ LAN still, right? So DMZ LAN. Set firewall name for the next one is going to be the DMZ LAN, which is the one that we just did. So DMZ LAN, and then the default action is going to be to drop, because that's basically all we're doing here, it seems like. The next firewall name is what we need to do is the DMZ WAN, right? Rule action, no, so DMZ LAN, I have 52 seconds. We'll do DMZ LAN. Rule 100 action is going to be rule 100 action. Rule 100 action. So it's not the default action, it's the rule 100 action. I'm going to do accept. So that's that. And then so the next one is going to be DMZ LAN, and rule 100 protocol in this case is going to be HTTP. Run it. Okay, interesting. So it gave us the thing right here. So it gives us the DMZ to the WAN now. That's probably going to be the next one that we have to do probably. And that one gives us another few minutes to run this thing, but it said DMZ LAN, what, it changed it. DMZ WAN, changed it again. DMZ LAN, or it changes by itself? Yeah, it is changing by itself. Okay, so HTTP is greenlit, TCP is not greenlit. It's blocked. That's what the current stuff is. So that was our setup right here. So you do the set policy zone itself. So it's from to where it's coming from first, and then what's the default action. So the DMZ default action is drop. The policy zone is from the DMZ to ETH010. And then that's the interface. Then you have another one that is for the LAN. So the LAN right here, the default action for that is also drop. And then the policy zone interface for that one is ETH020. And then you have the the firewall name at this point that we had to set up, which was just the DMZ to LAN, which there's no indication here, but based on what they showed us in the previous example right here, that's what they did basically. So wherever it was coming from, or wherever it's going to coming from, so its zone is LAN WAN, so LAN WAN, and then zone is WAN LAN WWAN LAN. That's the way that they did it. So if we're doing DMZ LAN is the entire setup for that, so it would be DMZ LAN for the firewall name for this whole thing. The description, DMZ LAN, the default action is drop for everything. The rule 100 action, which is different from the default action. So the rule 100 action was the accept part right here. And then DMZ LAN, being the specific one that we're dealing with over here, needed to be with the protocol for HTTP. So that's how that whole thing was set up. So that is that specific task for zone pair policies and filtering. So let's now go to validating network traffic. And I think is that another one that we do? No. So this is I don't think this has to do with that view site anymore. So let's look at validating network traffic now. The scenario here is the organization has proper zoning and routes in place. A zone pair between DMZ and LAN allows the HTTPS connection. Of course, the firewall should accept those connections. So how is Susie supposed to watch Facebook or Azure updates install, right? How could any of these things actually happen? So there's a threat actor that has landed an implant through phishing on a LAN machine. Assuming host defense mechanisms have failed, how can the implant be detected and monitored? If the beacon for the threat actor is using HTTPS through the DMZ, that would look primarily like legitimate traffic to the firewall and the analyst. So to solve this, we have to use a SSL TLS inspection to intercept the HTTPS connections. SSL TLS uses the SSL proxy to intercept protocols, including all of this stuff, or the other encrypted traffic. And once it's intercepted, the proxy decrypts the traffic and sends it to be processed by a unified threat management platform. The UTM will employ deep SSL inspection, feeding the decrypted traffic from the proxy into other services on the UTM, including but not limited to web filters or the intrusion prevention system to process that information. It seems ideal, but there are downsides probably. So some may have already noted that it requires an SSL proxy or a man-in-the-middle attack, right? So if a firewall or a vendor has already implemented the solution, it will act as a man-in-the-middle between your devices and the outside world. And what if it intercepts potentially plain text passwords? A corporation has to assess the pros and cons of this depending on the calculated risk. And you could allow all the applications that you know that are safe to prevent potential cons, but the solution will have disadvantages. An advanced threat actor could route their traffic through a cloud provider or a trusted domain. So it's not it's not foolproof, right? And we talked about this a few times in the last videos as well. There's nothing that's 100% foolproof. You can get pretty close to secure, but there's going to be certain things that you may have to either just accept the risk for or find other ways to get a workaround for it. The question is, does SSL inspection require a man-in-the-middle proxy? And the answer for that would be a yes, it does. What platform processes data sent from an SSL proxy? And that's going to be the unified threat management platform. So this was, it's an interesting concept. So validating the network traffic needs to go through an SSL proxy and get processed by a unified threat management platform. And those things connect to a bunch of other things. For example, your IPS, Internet Prevention System, or Intrusion Prevention System, Internet Prevention System, the Intrusion Prevention System to actually process that information. But again, has downsides because somebody can go through whoever your man-in-the-middle proxy is, and it could be a cloud provider. So if you say that a cloud provider is allowed to use or is allowed to pass traffic through here and we're allowed to access that, all the threat actor has to do is go through that same cloud provider, and now it looks like it's legit. So you need to put more rules on top of your rules. Like this is not a one and done type of a configuration. There's several layers to your security that need to be implemented for all of these things to work. And as you can imagine, it'll get fairly complicated, right? So this is, again, it's like this is an introductory concept to, or introductory overview of this concept. So let's look at addressing some common attacks here. Cisco defines DHCP, Dynamic Host Control Protocol, DHCP snooping, as a security feature that acts like a firewall between untrusted hosts and the trusted DHCP server. So DHCP server was introduced to combat rogue DHCP servers, and it's going to validate and rate limit the DHCP traffic as necessary. If a host is untrusted, the traffic will be filtered and rate limited. Although DHCP is a layer 3 protocol, dynamic host control protocol that deals with IP addresses, DHCP snooping operates on the switch layer, the switch at layer 2. The switch will store untrusted hosts with the least IP address, least as in not less than, least as in rented. So this switch will, the switch will store untrusted hosts with least IP addresses in a binding database, a DHCP binding database. The database is used to validate traffic and can be used by other protocols such as the ARP inspection. We'll cover it later. We know how DHCP snooping will gather and store addresses, but how does it determine what to do with that traffic? The list of conditions of the protocol will inspect to determine if a DHCP packet should be dropped. This is it. So any DHCP packet is received from outside the network. The source MAC address and DHCP client hardware address don't match. DHCP release or DHCP decline packet is received on an untrusted interface that does not match the interface, that the secure address, that the source address has already been registered, and then the DHCP packet that includes a relay agent that is not I think that's what the domain gateway address typically looks like. It's like 0000 or 1111, something like that. So DHCP, any packet is received from outside of the network. The source MAC address and DHCP client hardware don't match. So the source MAC address that is coming from this packet doesn't match the client hardware that we have on file. That's why it's called snooping. Snooping basically means that they've changed those things. And so if the release, or not if the release, a release or decline packet is received on an untrusted interface that doesn't match an interface that the source address has already been registered. So that's what this basically means. And then the packet that includes a relay agent address is not 0000. So these are the rules, right? These are the list of the conditions that the protocol will inspect to determine if the packet should be dropped or not. And so if any of these things are triggered, then most likely it's going to be dropped. So recognized by IE in several research papers, there is no standardization of DHCP snooping. That said, it generally does not change between vendors, unlike other protocols. Dynamic ARP inspection. So Cisco defines ARP inspection as a security feature that validates address resolution protocol packets in a network. ARP inspection will validate and rate limit ARP packets as necessary. If an ARP packet's MAC and IP address don't match, the protocol will intercept, log, and discard the packet. So ARP, address resolution protocol, works with MAC addresses, and then it connects the MAC address to an IP address, and that's how the whole thing gets filtered out. So ARP inspection uses the DHCP binding database filled from DHCP snooping as its list of binding IP addresses. So the DHCP binding database provides the expected MAC and IP address pair of the untrusted hosts, and the ARP inspection will compare the source IP address and the MAC address to the binding pair. If they're mismatched, it's going to drop the packet. So DHCP provides the MAC and IP of the untrusted host. ARP inspection compares those two to the binding pair that it has, and if they're mismatched, then it's going to drop the packet. This is the diagram showing a valid ARP request that matches both the binding and request information. So address resolution protocol, it's a request, hardware type, Ethernet, protocol type, IPv4, size is 6, protocol size is 6, opcode is request, the MAC address of the sender, right? And then the IP address of the sender. The target MAC address is nothing because it doesn't have anything in its database yet, and then the target IP address is filled in. And so that is going to turn into this. So all of that turns into this. You have the MAC address that you do know with the IP address that you do know, and then the number of seconds. DHCP snooping is the type that is going to show up for your security appliance on the VLAN that has the ID of 10, gigabit internet 1, right? And then this is the MAC address and the IP address, least DHCP snooping the ID of 20, gigabit internet 2. So this particular case is showing the valid ARP request that matches both the binding database and the request information. So in this case, this is, I guess, all valid right here. And then from here, the diagram showing an invalid ARP request. So you have the MAC address. So everything else up until this point is the same. You have the MAC address that in this case is missing some information. In this one, we actually had a filled in MAC address from what it seemed. Or maybe this is actually the MAC address in its entirety. This is the IP address that's attached to it, and that's the same IP address. And then now there's the IP address of the target, and it didn't serve well, so it was then denied. And DHCP snooping is still the type that came through with this. So really the only thing that I can see that is a difference between these two, and this, I don't think there's supposed to be a difference that we're supposed to pull. It's just that they're showing that this is what it looks like when it doesn't work, or when it is unverified, or what is it? Invalid. An invalid ARP request that does not match the binding database and requests information. Note the sender MAC address has been spoofed. So this was what I thought was going to be the case. So this just doesn't seem like a right MAC address, because the MAC address is supposed to be this, and this does not represent that. So the actual MAC address over here, this is the one that was valid. So this was the actual MAC address, and this is what it's supposed to be. Whereas in this case, this is what it's supposed to be, and this is what came through. So it's been spoofed. So I actually did have it right at first glance. I gotta pat myself on the back for that one. Where does DHCP snooping store the least IP addresses from the untrusted hosts? It is going to be inside the DHCP binding database. That's where it stores it. So we're going to paste that over here, and my keyboard needs to connect. There we go. Will a switch drop or accept a DHCP release packet? It's going to drop it. Does dynamic ARP inspection use the binding database? Dynamic ARP inspection. Does it use the binding database? ARP inspection uses the DHCP binding database. So that is a yes. Dynamic ARP inspection will match an IP address and what other packet detail, and that would be the MAC address. And there we go. And we got our addressing common attacks task done. And that was it for securing network architecture. And there's nothing really in the conclusion other than just what we went over. And to continue exploring this, we're going to go through network security protocols, which is going to be is it down the line here? Network security protocols. Yeah, it's inside the current module that we're going to be dealing with, but let's not jump ahead here. So we have completed 8 today. This is episode 9 that we're on, and we just wrapped that. So episode 9 in the bag. If you are studying for your security engineer, SOC analyst, Pentest Plus, security analyst, ethical hacker, any of those things, I do invite you and recommend that you actually like and subscribe and turn on that notification bell, because all we talk about on this channel is cybersecurity, ethical hacking, pen testing, engineering, all that stuff. And all of these things are going to be applicable to you for your studies and your certification exams, as well as your day-to-day job in any of those roles. And on top of that, just as an extra bonus for me, it would be really nice to have you as a part of our community. And I do my very best to make sure that I post consistently and answer all the comments to just make sure that you get as much value as possible as being a part of our community. So it would be awesome to have you, and I think you'll actually get a lot of value from it. It's your boy Hank Hackerson at Hank Hacks Hackers, your favorite network and system attacker / protector. And, love, peace, and chicken grease. If no one else loves you, Hank loves you. Hope you enjoyed this one and you got a lot of value out of it. I will see you in the next video. Peace.